right, so 6.2 notes. This is part B. Yesterday we just did part A, which was just graphing sine and cosine. So just graphing sine and cosine is foundational to being able to do any of the rest of this. So that sheet that you had yesterday with the graphs of sine and cosine are going to be really important. I can already tell you right now that whenever we get to test time for this, which is still a little ways away, you will have, on that test, you will have a question that just asks you to graph f of x equals sine x. And so when you do that, what you need to remember, no matter what, I mean, it should be, you should have a 2 pi right here. It should have a period of 2 pi. Sine of x has a y-intercept at the midline on that x-axis, and then it's going to go up, middle, down, middle. And then the pattern will continue over here. So you will definitely see a question that just asks you to graph sine x, and it will be multiple choice. You won't have to graph it by hand or anything. So you need to be able to recognize sine of x. You also will have to be able to graph cosine of x, which we got 4 little tick marks here. That's 5. Cosine is almost the same, except for it's going to have a y-intercept at a maximum point. And then so maximum, midline, maximum, minimum, I'm sorry. Maximum, midline, minimum, midline. And so I'm using that word midline before I've taught it to you, but I bet you can guess what that's going to mean there. So you'll need to be able to identify both of these graphs, because you will have some that just ask you to graph these without transformations. Because if you can't graph these, you're not going to be able to answer the other questions, right? So this is really important. We copied it down on that page yesterday. Make sure you're familiar with those. So let's just do a quick review. All right. So I'm on. So translations. I told you guys yesterday, everything that we're going to do is not really that new. There is one thing I didn't make you do with regular functions, but all of the transformations for trig functions are the same as the transformations for the other functions, just some of them are going to have different names for trig functions. So if I have x squared plus 3, Reese, what type of graph do I have for that one? All right, the square tells me that I'm dealing with a what? Quadratic. And then, Reese, what does that plus 3 do to that quadratic? Up 3. Okay, so that number added or subtracted out there on the end moves that graph up or down, right? We call that a vertical shift or translation. Vertical shift or translation. All right, so that's just going to move that graph up or down. It goes the direction that you think it should go. A plus will move it up. A minus will move it down. All right, but then if we look at the second one, we've got x minus 5 to the third. Grace, what type of function are we dealing with for that second one? Yeah, cubic. Very good. And what has happened to that cubic, Grace? Right 5. Very good. And that we call it horizontal shift. And remember, anything inside of the parentheses, that's going to be horizontal, whether it's moving it left or right, or stretching it out or shrinking it. If it's inside of the parentheses, it's going to affect the x-axis, and everything's going to be opposite. So if we have a minus 5, it's actually moving it to the right 5. Okay. So you guys remember those rules? Hopefully that's a quick refresher on that. So we're going to deal with translations with trig functions. They are going to be very similar. So if we have something like sine of x plus 1, that's just a sine function that's been translated up 1. So there is a term that we need to know there's a term that we need to know for this that is called the midline. Now, midline only applies to trig functions. It doesn't apply to quadratics or cubics or anything of that nature. Midline is the horizontal line that is halfway between the maximums and minimums of the function. Right, so just basically the line that goes through the middle of the graph, right? Like it kind of sounds like. So if we just have the original function sine of x, what is the midline for that? What's the line that goes through the middle of that? It is, oh, I love that you guys said y equals 0, which is also what word, like what name could we give that? What is it called on that graph? Y equals 0 is the x-axis. Most time students say x-axis and then have got it mixed up on the, they call it x equals 0, but y equals 0, or the x-axis here. So if we move this up, it's going to make that midline go up. If we move up 7, the midline is now going to be y equals 7. If we move it down 3, the midline is now going to be y equals negative 3. So it's just shifts it up and down. In my opinion, midline is one of the most simple ones to find for these problems. I think they should be pretty straightforward. Most students do not have trouble with midline. All right, horizontal shifts. Horizontal shifts can be very simple unless they also have horizontal expansions or compressions. So we're going to learn the simple version right here, and then I'm going to tell you about the more difficult version here in a second. All right, so f of x equals cosine of x plus pi. This would be the cosine function that has been shifted to the left pi units. For trig functions, there's just something I want to tell you about this right now, and then we'll learn something else about it later. A horizontal shift has a special name for this. A horizontal shift is also called a phase shift. You will find that horizontal shifts are a little bit more difficult to see on the graph with trig functions. And let's think about why that is. I'm going to pull up Desmos real quick here. Keep those. If I pull up Desmos really quickly, if I have a horizontal shift, if I have f of x equals x squared, a horizontal shift for that is really simple to tell that, oh, that's slid over to the left 2 units, right? It's very simple to see that. But if I have sine of x, it becomes a little bit more difficult because if I, for example, if I do sine of x plus 2 pi, I shifted this graph to the left 2 pi, but does it look any different at all? It's the exact same graph, right? My red graph, if I click on my red graph and my blue graph, there's the same graph. Because what's happened is as we slide that left to right, it's eventually, because it repeats itself, it may end up on top of where it was. So, for example, if I only shift it to the left pi, that's a cool graph, I like to look at that. If I only shift it to the left pi, it's a little difficult to see. It kind of looks like I just reflected it over the x-axis, and in fact, you could just reflect it over the x-axis, and it would give you the same thing. So if I do negative f of x, you can see it's the same as x plus pi. So the phase shifts are a little bit more difficult with this to see when you're looking at a graph because these graphs like end up on top of themselves. This is, so it'll be a little bit different. We'll look at those more here in a little bit. Also, it also says right here, we will learn one more thing about horizontal shifts at the end of this section, because they can be very simple if they are just horizontal shifts by themselves, like we see here. We just go left pi units, but they can also be much more difficult. So we'll, when I say much more difficult, there's a formula for it you need to know. It's not like, it's not super difficult, but more difficult than this. All right, so let's talk about expansions and compressions.
We don't like those.
I know, they make things difficult, don't they?
Let's just do horizontal and vertical shifts.
Yeah.
Y'all agree? Raise your hand if you agree.
Are you just starting to mutiny against me? To
Yeah.
just refuse? They are difficult. Then whenever you got that horizontal expansion or compression with a phase shift, you gotta do C over V. Alright, so I don't really know whenever I made these notes why I made those negative. What's the negative inside going to do? It's going to flip it over the y-axis, and I don't really know why I put that on there. So the better question is, after I've done this so many years, why don't I go and take it off? But I never do. It's been like 3 or 4 years that I do this. So that would be a reflection, but really I'm only concerned right now with expansions and compressions. So let's talk about those first. So expansions and compressions are the trickiest when we're dealing with functions. So for this first one, Connor, I've got a 3, and it's on the outside of my absolute value bars. What is that going to do to the graph? It is going to make it thin. But when we think about it, it's vertical expansion. So it's actually, it's kind of like, it does look thinner, but it's because you're stretching it vertically. Like, if we could just take, somebody and stretch them vertically, they would look a lot skinnier, because they would be so tall. So, so this is a vertical expansion by a factor of 3. So when the number's on the outside of the bars, that's vertical. Everything on the outside deals with the y-axis, right? It either moves it up or down, or it's going to stretch it vertically or squish it down vertically. So whenever we see 0.25 absolute value of x, Maddox, what's that going to do? Fourth, right? And it's going to compress because we've got a small number there, a number between 0 and 1, and it is on the outside of the parentheses. Okay? So that leaves us the last two where we have our numbers multiplied on the inside of the parentheses. So, Caitlin, what would we have for the third one there? Very good. Horizontal. Compression. And what factor would that be by? Perfect, 1/2. So if we're compressing our number, our factor needs to be small. So it's 1 over that number, not just that number itself. And then, Grace, what would we have for the last one? Very good. Horizontal. And what would our factor be on that one? Or how would we find it? It's always 1 over the number, right? So here it was easy because it was just 1 over 2. We didn't have to do anything special with that. But this one is going to be 1 over 0.5, and we know that I probably am not going to let you leave that decimal in the fraction because that's just kind of ugly. So that would be 1 over 1/2. Dividing fractions is easy as pie. Flip the second and multiply, and so you would get 2 for that. So horizontal expansion by a factor of 2. So trig functions are going to work the same way. They're just going to have a few different names that we're going to talk about these with. So let's start with amplitude. Okay. So amplitude is the distance, or let's call it the vertical distance, vertical distance from the midline to the maximum point. Or I could change the definition and say from the midline to the minimum point, because that should be the same distance, right? It doesn't really matter. There. So it's the distance from the midline to the maximum point. So whenever we take our graph and we stretch it vertically or shrink it vertically, it's going to change that amplitude of your graph. Amplitude is a word that you'll hear a lot whenever you're talking about waves. So like in science class, whenever you're talking about different amplitudes of waves. Sine graphs, you can see them. They're wave graphs, right? So that amplitude is going to be this number in front of your sine or cosine function, right? It's going to tell you how tall or short your wave is. If you have y equals a sine x, then absolute value of a is the amplitude. Notice that they put absolute value bars right there. This tells us amplitude is always positive. So I didn't do this in an example, but let's say like this last example right here was negative 130. We would not say the amplitude was negative. Amplitude is always going to be positive. What does that negative do if we have a negative out front? What do negatives do to our graph? They flip it upside down. So we want to think of that negative separate from the number out there. So the negative does do something. It's going to flip your graph, but it's not going to change your amplitude. So amplitude is, most students find it very simple to find. It's just the number in front of your sine graph. So if you had y equals 3 sine x, your amplitude would be 3. If you had y equals 1/2 sine x, your amplitude would be 1/2. If you had y equals negative 130 sine x or positive 130 sine x, would not matter. Your amplitude would be a positive 130. Okay, so it's always going to be positive there. Okay, here. Okay, horizontal is always more complicated than those vertical, right? Vertical, even with our other functions, was easier than that horizontal. With trig functions, it's going to be really important. We really have to know how to do these horizontal expansions and compressions. But it's a little bit trickier than just amplitude. Amplitude and vertical shifts, most students, like if you don't know how to find amplitude and vertical shifts, then you probably do not know how to do anything whenever it comes to graphing trig functions. But period and horizontal shifts or phase shifts are going to be a little bit more difficult. But they're, as long as you know the formulas for how to find them, they're really not that bad either. So the period of a graph is the amount of, I'm going to call it time, but let's think of the x-axis there. X-axis is a lot of times it's time, but it's not always. It takes for the graph to repeat. Okay, so we talked about our sine and cosine functions yesterday, and we talked about that. We talked about that term period. What was the period for our just basic sine or cosine function? 2 pi, right? And it makes sense because it's related to that unit circle. 2 pi is all the way around the circle. So if you go all the way around the circle, you're just going to start repeating after that if you keep going around the circle, right? So, if we do not have a shift, if we do not have an expansion or compression, then the period of the function is just going to be 2 pi. But if we have a number right here inside of our trig function that is multiplied by our x, it is going to cause us to have a change in the period of the graph. Because if you think of, let's go back to Desmos really quickly, because I like to look at what this looks like. If we think of our graph of sine x, if I do 2x or 3x or 7x, it squishes it in. Think of it like an accordion, right? And then if you do like 0.5x or 0.1x, ooh, 0.1x, we may have to zoom out a little to see that. So that really stretches it out, right? So think of it like an accordion, squishing it in or it's stretching it out. Whenever you do that, it changes the period of the graph. Let me go to 0.5 again so that I can see it a little better. So if I look at this graph, let me show you this on Desmos also. If you go to graph settings, because we're going to be doing most of this in radians, to practice those radians, I would really like for my x-axis, instead of being in terms of 1, 2, 3, 4, 5, I would like for it to be like pi over 2, pi, 3 pi over 2, like we see on the unit circle. So you can get Desmos to do that for you. If you go over here and change your step to something like pi, or pi, it'll kind of automatically adjust. So if you click that wrench button and over here where it says step, change it to pi, and then it'll be in terms of pi on your x-axis. Or if you specifically want something like pi over 4, you can do that, and you still would have to zoom in a little bit for it to, it automatically adjusts that. But so if I see here this red graph, my basic graph, it takes until 2 pi for it to repeat. But if I stretch it out, now, right here, my blue graph, if I look for when it repeats, at 2 pi, it's only halfway there, right? And I have to keep going, and it's 4 pi before it starts to repeat. So when we have that expansion or compression, like the accordion, it is going to change our period. So it's pretty simple to find the period. All we have to do is we have to take the normal period for, go back to, we take the normal period for sine and cosine, which is 2 pi, and we divide it by whatever number is in front of our x there. So 2 pi divided by b. So if we were asked to find the period for sine of 5x, all we would have to do is we would take 2 pi and divide it by 5. In this case, that won't reduce, so you would just leave it 2 pi over 5. So that means if I have 5x, it should, at 2 pi over 5, it should start repeating, right? From 0 to 2 pi over 5, my graph should start repeating after that. All right, if I have cosine of 1/2 x, then, Braden, what would I have to do for that one? Perfect. So 2 pi divided by 1/2, dividing fractions, easy as pi. Flip the second and multiply. It's just like multiplying by 2, so we'll get 4 pi. And if you think about what should be happening here, a big number compresses, so that period should get smaller. 2 pi over 5 is smaller than 2 pi. A small number expands, your accordion's being stretched out, so that period should be larger than it was to start with. Okay, questions? Okay, so let's talk about the phase shift. And so this is something I never made you do with with quadratics. I probably should just start including it, but it's a little tricky and I didn't want to. But we definitely have to know how to do this with phase shifts and periods, because with trig functions you really can't avoid having both of these sometimes, especially if you're trying to model real life situations. So when your period is not 2 pi, it affects your phase shift. Okay, so whenever we have a number in front of our x or our theta here, and then we have a phase shift also where we're shifting left or right, it is going to affect the phase shift. So for y equals sine of bx plus c, there is a phase shift of c divided by b in the opposite direction, right? So our phase shift, if we have a number right here in front of our x, we're going to take this number that tells me how far I shift left or right, and I have to divide it by that number in front of the x. Okay, we did not see any of those when we were doing these. We didn't see that combination when we were doing these. But if you keep that formula in mind, it's pretty straightforward. So if I want to know, this asks me for period and phase shift. So let's do period first. That was what we just did on the last slide. So Blaine, if I want to find the period of cosine of 2x plus pi, what would I need to do? 2 pi. Yeah, 2 pi divided by 2, which will just cancel the 2's, and we'll just get pi for the period there. So our period would be pi here. And then our phase shift, we would need to just take our c value right here, which is pi, and divide it by the number in front of our x, which is just 2. So it would be pi over 2, and since we have a plus sign right here, it would be left, go opposite direction. Sometimes you'll see it given with like the actual word for the direction. Sometimes they'll just call that negative pi over 2 to show that it goes to the left pi over 2. All right, questions? All right, so Hallie, what would we do to find the period for the second example there? 2 pi over 1/3, and dividing fractions is easy as pi. We will flip the second and multiply. What will we get for our period on that one, Hallie? Perfect, 6 pi. And then our phase shift, Bronwyn, what will we do to find our phase shift here? So if we look back at the last one, we took pi, which was our c value, that number right there, the number that was added or subtracted, and we divided it by the 2 that came from right here. So if we're doing that same thing here, we got, this would be our c value, and this would be our b value. So what would we do for this one, Bronwyn? Perfect. 9 divided by 1/3, and dividing fractions is easy as pie. Flip the second and multiply, and we will get 27. So it'd be 27 to the left here. Okay. Questions? All right, so let's summarize a little bit here because let's put all of this together. So it really, what you do with shifts, it does not matter whether it's sine or cosine. The only difference between a sine graph and a cosine graph is that you're starting with that either sine where it has a y-intercept at 0, 0, or cosine where it has a y-intercept at 1, 0, right? So, but as far as finding period, amplitude, midline, phase shift, your formulas are the same for either one. So if we want to find the period of a graph, we are just going to do 2 pi divided by the b. There. Amplitude is just going to be absolute value of our a. Midline, that's that line in the middle. It's going to change when you shift up or down. So it's just y equals d. And our phase shift is going to be, I'm going to put a negative c over b. The negative reminds us that we're going in the opposite direction, right? There. So you can either give that with a like positive or negative sign, or you can tell it left or right. There. All right, so this you need to know really well, right? Well, certainly right now, you're probably going to need to have it handy so you can refer back to it. But eventually, which it will be next week before we get to quiz time on graphing this stuff. But eventually, you are going to need to have all of this memorized so you just know off the top of your head how to find each piece, right? So make sure that you have that. So let's just do a few examples. All right, so we need to find period, amplitude, phase shift, vertical shift for each of these functions. So period, amplitude, phase shift, and vertical. Actually, let me add something. Well, I'm going to change vertical shift. Let's change that word for vertical shift. Vertical shift, it is possible for us to say we do not have a vertical shift. But a lot of times, instead of vertical shift, they may ask you for the midline. So I'm going to change vertical shift to midline. Okay, so something really important here, you should, oh my gracious. He about gave me a heart attack. Is he cracking? Should we report, do we need Miss Mullis to report down to Coach Wood's room right now? If he was really, I feel like in a really Ricky Bobby situation here, he's probably going to fall off of the roof. And he's going to be in the hospital, and his wife's going to tell him to pull the plug. I've thought about a lot. I just want you guys to just go ahead and pull the plug. I don't think he's ever done that before. Just at this door. I don't think he's been on the roof before. Huh? You cannot get on the roof, no, Connor. Is he still out there? Huh? Okay. I don't know. I don't know our school's roof. Now, Miss Gillamall, I have seen Miss Gillamall on the roof before. She used to be in Miss Felt's office right here. And she was on the, I think it was her. Somebody was on the roof from, I think she was like cleaning the windows off, or something of her room. She was out there one time. I'm pretty sure. Yeah, I'm going crazy because I feel like this happened, but yet I feel a little uncertain when I say that maybe I did make that up. I know for sure they were out there working on the roof one time, and whoever, the workers that were out there on the roof looked young, and I thought they were students, so I fussed at them for being out on the roof, and then I looked down, and then I realized, like, the other worker, he did not look like a student, and I was like, oh, wait, you guys are just working on the roof, aren't you? So I did embarrass myself doing that one time. Coach Wood, I don't know what he's out there doing. And those are those his students wandering around with the same headphones on? What kind of, I bet they're the ones they use during football, aren't they? I bet they're the ones that they use during football to communicate to the coaches. And surely he hasn't let his students out on the roof. Maybe he's getting closer and closer to retirement. So he's becoming a little wilder every day. So you could not get on the roof. Please, you listen. And I am maybe so. I am not in charge of telling you whether or not you can walk on your own roof at your house. But as soon as I authorize you out there on that roof and you fall off, so please be careful on a roof. So this makes me think about that daggone Ferris wheel I've been reading about. How in the world did that man make this Ferris wheel? The first Ferris wheel was as tall as any building they had built in the world at that point. Like, it was as tall as the tallest building. And they just decided, like, they weren't like, hey, we'll make a small Ferris wheel, like, 30, 40 feet in the air. People will love it. They're like, no, we're going to go as tall as what they were calling skyscrapers at that point, that were like 260. Oh, how many people should ride on it? 2 people per seat? No, 60 in a car. 2,000 people at one time in a giant Ferris wheel that we don't even know if it's going to work because nobody's ever made one of these before. And they're like, let's go for it. That was a different time, wasn't it? I couldn't even imagine. It was definitely a different time. Because I had never known that the first Ferris wheel was something of that magnitude. There were no roller coasters. There were no, thrill rides at that point. Can you imagine those people were that in the book it tells about this one man that apparently was super afraid of heights, and so he had some sort of crazy panic attack while he was up there, and just started throwing himself against the sides of the car and trying to escape even though he was at the top in the air, and they had to tackle him and tried to hold him down because they were afraid he was going to actually be able to escape.
I was trying to think how long Junior stick my nose in the screen. We just Ricky, his best friend. My best friend.
Oh, I get what you. Yeah. Connor wanted to go out there and talk to you, but I told him he couldn't. Anyway, but and they had put locks on it so that people couldn't accidentally fall out, but they had not made it super, they hadn't made it. They were afraid that he was actually bending the bars and stuff, and so eventually the problem was solved because it says that a woman took her skirt off and put it over his head, and sat there and rubbed his head and told him to calm down, and that worked. which was also very, very risque at the time. Yes, but well, it's a great book. Eric Larson wrote it, and he also wrote Isaac Storm. Have any of you ever read that one? Sometimes they'll assign it like in high school, but I love Isaac Storm. It's also super good. It's a crazy story too about how nobody knew hurricanes were coming 100 years ago. So in Galveston, Texas, like a Category 5, I don't know, a huge hurricane hits Galveston, Texas. Nobody knows it's coming because we don't have radar and we don't have all of that. And so like the whole island is like underwater. And, I mean, now everybody knows a hurricane's coming 2 weeks ahead of time. And if it looks really bad, those who can try to evacuate. There's not really that many people left. Causes a lot of damage, but usually hurricanes don't take that many lives. Galveston, Texas, in the early 1900s, like 6,000 people died from this hurricane. It's like crazy. It's also a great book. You should read it. But anyway, this book is, it's like the fair is going on, which is like this grand, like, world thing that, like, nothing has ever been done like this before. Yet at the same time, you've got this serial killer over here that's like, so it's kind of like the great, like, it's like a huge, I'll call it advancement in, lifestyle in America with all this, like, extravagant entertainment and stuff. At the same time, you've got, like, this evil at the same time. It's like, so it kind of follows both stories at the same time. So it's a really good book. You guys should read it too. But anyway. We might do some Ferris wheel pumps. This we're way off topic. Coach Wood has derailed me here with his stunt. All right. So one thing we need to know about this: there should always be an answer for for 3 of these 4 things. The only thing you can ever say none to is the phase shift. So it may not shift left or right. In fact, does this one have a phase shift? It does not, because if we had parentheses, they would be around that X right there. So it's not been shifted left or right. Everything else has to have an answer here. So we're going to say none for the phase shift. But everything else always has to have an answer. So are there any changes in the period for this graph? Is there a number in front of that X right there? There's not. So there will be no changes in the period, but the graph still has a period. So the period of the graph is 2 pi if you don't have a number in front of your X. Okay, so it's just that period is how long it takes for the graph to repeat. So if you have not done the accordion with it, if you not stretch the B number right there, that's your accordion number, right? It stretches it out or shrinks it in. So if you haven't done that, it just stays where it's at. Amplitude, you will always have an amplitude. Grace, what is the amplitude for this one? It's 3, right? That's our vertical shift. That's how tall our graph is. You will always have an amplitude. If there's no number there, it's 1, right? And then midline, you will always have a midline. If you don't have a vertical shift, then it's just y equals 0. It's just the x-axis. But if you have a vertical shift, as we have for this one, Maddox, what would our midline be? 4. So we'll say y equals 4 because that's going to be the equation of that line there. So you should always have an answer for period, amplitude, and midline, no matter what. These always have an answer, even if I just give you the graph of sine x that's not been translated at all. Phase shift, sometimes you're going to say none for that. All right, let's do the next one. Okay, so Summer, what would the period for this one be? There is one, but it doesn't change, right? So it's just going to be 2 pi. So you'll always have one, but this one doesn't change, so it's just 2 pi. So if there's no transformation, you just put 2 pi. Let's see, Jackson, what's our amplitude? Very good. Okay, let's see, Reese, do we have a phase shift for this one? Okay, it's that number added or subtracted on the inside because that's going to shift it left or right. And so phase shift is always C. Let me highlight here. C over B. B is the number in front of X, but we don't have a number in front of X, right? So in this particular case, it's just going to be, I'm still with a highlighter. Let me go back to the pen. It's just going to be 3 over 1, which is just going to be 3. And will it move to the right or the left? Right. It's opposite direction. So if you have a minus, you want to go to the right. So look at this sign right here with that 3. If it's a minus, it'll go to the right. If it's a positive, it'll go to the left. So it's opposite sign. And then midline for this, let's see. Caitlin, what would the midline for this one be? Very good. There is no vertical shift for this, which means the midline doesn't move. It's just the x-axis there, y equals 0. Yes?
If there's no addition to the cosine, it's always just 1 for the midline, right? Or is that?
Midline is, no, it's 0 still. It's also 0. That y-intercept is going to be 1. So the y-intercept, you would start from 1, but usually they'll ask about midline instead. So midline is 0 for both of them. That's that line that runs through the middle of it. Good question. Okay, here's a couple more. We need period, amplitude, phase, shift, and midline here. So, Connor, what would the period be for this one? Just pi. Because we will take 2 pi, and we will divide it by our b value, which is that number in front of the x. So 2 pi over 2 is just pi. Okay. Reese, what's our amplitude? 2. Just that number in front of sine. Blaine, what about our phase shift? Not quite. It's going to be left 4 divided by 2. So for phase shift, because we do have a number in front of that x there, we've got to take this, oh, wait, that's not a highlighter. We'll undo it. Well, we take that 4 right there. Highlighter. Oh, black highlighter. I'm messing this up so bad. Alright, let's see. Let's just let me erase right here. Okay, let's try this again. Let's go to the highlighter, but let's not make it black. Let's make it yellow. Alright, so we take that 4 right there. We got negative 4 over 2. So that 4 is the number we put on top, and we have to divide it by that 2 that is our b value there. So whenever we do that, we are just going to get to the left 2. Sometimes you'll see it left 2. Sometimes you'll see phase shift of negative 2. It's fine. There. And then, let's see. Jackson, what's our midline for that one? Y equals 0. It's not shifted up or down any, so it's like you got a plus 0 out there on the end. All right, let's do the next one. Okay, so let's see. Noelle, what would we do to find the period here? Don't look in front of cosine. You gotta look in front of the x. Very good. And that one won't reduce, so we'll just leave it like that. Summer, what would the amplitude for this one be? There is one. Everything should have an answer except for phase shift. So there is no number in front of cosine, but what number could we put there that would not change anything? 1. So we got an amplitude of 1 there. So phase shift is the only thing we can ever say none to. The other ones, there'll be an answer. You got to think about what number you could put there without it changing. All right. Grace, what about our phase shift for this one? It'll be 2 to the right, because we'll do opposite of 6 divided by 3, which will give me 2 to the right. Okay, so we're taking, again, that's the one that sometimes students get the most mixed up with. So we're taking that 3, it goes on the bottom. We're taking that 6, it goes on the top. And last one for that, Maddox, what is our midline for that one? Perfect. Y equals 4. All right. We are not going to do that part today. We're also not doing that